Hello everyone, my name is Jeanfed Ramirez, and today I'll present you the work Hugo, Escalante, Villaseñor-Pineda, and myself entitled Sequential Models for Automatic Personality Recognition from Multimodal Information in Social Interactions. Now, I know this is a long title, but essentially I'll be focusing in personality recognition, and multimodal information. So here you go. Well, recognizing personality in an automatic manner is nowadays an active task in the affective computing field. So it has become very active, and its objective is to find patterns of behavior present in social interactions. But first of all, how do we quantify the personality? Well, there's self-assessments such as the Big 5 personality traits tests, which is also called OCEAN for the acronym in English, for openness, conscientiousness, extraversion, agreeableness, and neuroticism. So with these 5 traits, psychologists can assign a numeric value to each of one. And for example, for the neuroticism trait, someone who has a high value is considered someone secure, somewhere confident, and someone who has a low value, a low score, is considered someone sensitive or nervous. And participants or persons who want to quantify their personality, they respond these tests, and they get these 5 values for themselves. So our task here was to recognize personality from individuals based from video sessions between dyads. So a dyad is considered a synonym of a pair of individuals, and our approach was based on experimentation based on the UDIVA dataset, from which we derive sequences of information, and we use these sequences as input for a recurrent neural network architecture that fuses this information and, well, predicts the personality. The state of the art over this data set includes one approach who separated participants in genders and extracted 1-minute chunks of information. And using this, they obtained 10 optimized multi-layer perception architectures using an AutoML technique called neural architecture search. So this was one approach. Another approach used transformer architectures, and they computed cross-attention between modalities and between participants. A more detailed description about the dataset, it's called UDIVA version 0.5. It was part of a challenge at the ICCB, and it contains 145 dyadic sessions. It is a multimodal dataset, so it includes video, transcriptions, and some metadata. And the participants here perform competitive and collaborative assignments, such as playing board games and talking. And the type of problem here is to predict the personality of these participants. So it is a regression problem, since I told you that personality is quantified using the OCEAN, the 5 scores. And the evolution metric, thus, is the mean square error. Here's the overall model architecture, and I'll explain to you in the next few slides. For the first part, we extracted features using pre-trained models. In this case, for each of the modalities, we use a pre-trained model. For example, visual landmarks, and text modality, fast text word embeddings, and for the audio modality, some other embeddings from the BGG-ish network. And the first approach was to generate these sequences using a predefined time window of 3 seconds. So we represent the information from these 3 seconds in one vector, and like this we generate a sequence of vectors of information. And the second approach was using a dynamic time window, which is computed by computing all the mean, computing the mean and the standard deviation of all the vectors that occur in an utterance. A utterance is like when a participant says something. So with this other approach, it's how we tested our model. And we used recurrent neural networks and AutoML to search for the best architecture. And the number of vectors we used it as input was 10. So here, finally, to obtain the personality of an individual, we all the samples we get from this individual, we pass it through our model, we get the predictions, and we aggregate these results to get a definitive prediction. We'll just computing the mean of all the predictions for a participant. Here's the recap of the model architecture. And well, here are our results. This is for the time window of 3 seconds. Here we have each of the traits in the columns. And this is the mean square error and the aggregated, which is used for a comparison, a direct comparison between the models. And here are all the models we tested under individual modalities and combined it. And here are the results with utterance approach. And what we found is that for almost every model that used the utterance level approach, we got better results and a better performance with these models. And in comparison with the state of the art, and these 3 works I mentioned, we outperformed them in 2 of the personality traits predictions. For example, in the extraversion and the agreeableness. So these models got a better result, and one of our models in the aggregated mean square error using the utterance level window got a better result than a transformer approach, which is encouraging for us. Finally, this is a qualitative result, which here in the x-axis are the traits, in the y-axis are the scores of the personality, and we have the ground truth values as in green and our predictions in red, and we found that this that happened to us happens also in the state-of-the-art approaches, which is that the predictions tend to the mean of the values in the ground truth test. So it doesn't capture like persons who are really extroverted or really introverted, or well, these values these models doesn't capture them. And as a conclusion, different from state-of-the-art works, we sample at utterance level, and our models shows better results using the textual and audio modality jointly and separately. And this outperforms some of the state-of-the-art approaches in two personality traits, and there's still much work to do. So we plan to solve this regression to the mean problem I just showed you in the plots, and this could be solved, we think, by using a different inference mechanism, not just aggregating all the predictions with the mean of them, but using another mechanism. And we plan to use or test also a lightweight transformer architecture that uses this multimodal information, and just to check if using this utterance approach could get better results than the others which use a predefined time window. And well, that's it. Thank you for your attention.